So, we're picking up where we left off on Friday. We just learned about solving for the frictional force when you're given the force of friction. Okay, so things we know about this problem. Okay, we've been given the mass of an object, which was 20 kilograms. Can't really see my decimal point there, but. And we were given the coefficient of kinetic friction. So, mu sub k, all right, which was 0.225, okay, and that's a ratio, so that's why it doesn't have a unit, okay, and then we were not given this, but it is a known factor. We know the force of gravity is 9.81 meters per second squared. And what we're trying to solve for is the force of kinetic friction. We don't know that one, okay? So we can use the equation force of kinetic friction is equal to the coefficient of kinetic friction times the normal force, okay? And if you remember, normal force is equal in magnitude to the force of gravity. So it would be mass times gravity subbed in for the normal force, which is why it's important that we know gravity. Okay. The reason gravity is not shown as negative here is because while the force of gravity is down, the normal force is up. So it will be opposite in sign. So we can then use the stuff we know. So what we should wind up with is we can solve for the force of kinetic friction if we take 0.255 times 20 kilograms. This is really terrible. I have a very hard time writing on this iPad. Hang on. I'm just gonna wipe this for a sec, and then I will write it out a little bit bigger. So the force of kinetic friction can be equal to mu sub k, the coefficient of kinetic friction, times the mass, 20 kilograms, times the force of gravity, 9.81 meters per second squared. And if you do all that math, what you should find is the force of kinetic friction is equal to about 50 newtons. That was our warm-up. Now we're really going to think, okay? The second example problem is a student attaches a rope to a 20 kilogram box of books. They pull with a force of 90 newtons at an angle of 30 degrees to the horizontal. The coefficient of kinetic friction between the box and the sidewalk is 0.500. Find the acceleration of the box. So go ahead and try this one on your own. I'm going to set a timer for about 2 minutes. In 2 minutes, I will do the setup, so drawing all the known and unknown values, and then in about 2 minutes after I draw the setup, then we'll work it together as a group. Okay? Things we know. We know the mass of the object, 20 kilograms. We know the coefficient of kinetic friction, 0.500. And we know the applied force, we'll call that force A. That's 90 newtons at theta of 30 degrees. So what we're solving for is acceleration. We don't know that. It helps to start with the correct coordinate system. So in this case, a great coordinate system would be to put the normal force pointing up. So this would be normal force. Force of gravity pointing down. We know those are going to be equal and opposite. And then we know the force of kinetic friction is going to be going in the opposite direction to the applied force. So we can put force of kinetic friction here, and we know that that's going to be smaller than the applied force because the box is moving. That's why I've drawn it as a smaller arrow. And then it's nice to put this in this direction because then we, or on this coordinate system, because then we only have to resolve one force, and that's the force applied. Okay, so force applied, we know this angle right here will be 30 degrees then, and that this strength of this force is 90.0 newtons. So now we have all of this stuff. What's probably our next step? Any guesses? Precisely. Next step, resolve that applied force into applied force X and applied force Y. So we know how to do that. We've been doing that for quite some time. You can do the force applied X by doing 90 newtons and then the sine of, or not sine, sorry, cosine of theta, and you can do applied force Y by doing 90 newtons and the sine of theta. Again, messy, I apologize for the lack of writing room on here. So go ahead and get yourselves that far. Okay, so when you work those out, what you should come up with is the force applied in the Y direction should come out at roughly 45.0 newtons, and the force applied in the X direction should come out to roughly 77.9 newtons. This one is to the right, and this one is up, which is why they're positive, because in the coordinate system that we have selected, both of those directions are positive. Now, the next step is we're going to solve for the normal force. Normally, normal force is equal in magnitude to the force of gravity. But we know that there are, in the x-axis, the force of gravity down, the normal force up, and some applied force in the up direction as well, which is going to change our normal force because it's going to alleviate some of that force of gravity. So to solve for that, we're just going to put what we know about objects in equilibrium, because this box is not moving up and down, right? According to the question, it is only moving to the right. So even though you're applying a force upward, in the in the Y direction, this box is at equilibrium, which means the sum of the net forces acting on it must be 0. So, assuming that, we can say that a sum of the forces in the Y direction is equal to 0, which is also equal to the normal force plus the force applied in the Y direction minus the force of gravity, because it's negative, because it's going in the opposite direction, in our negative direction on our coordinate system. So we know the applied force in the Y direction. We just solved for it. That's 45.0 newtons. We can solve for the force of gravity because we know the acceleration of gravity and we know mass. So we can take, to solve for the force of gravity, 20.0 kilograms times 9.81 meters per second squared, and come up with 196 newtons. So if we then drag this number up in here and solve for the normal force, what we'll get is that the normal force is equal to negative 45.0 newtons plus 196 newtons. So our normal force is going to come out to be about 151 newtons. Okay, now we have our normal force. So now we can solve for the force of kinetic friction that's opposing our applied force. Okay? That's the next step because we need to know the force of friction so we can subtract it from our applied force so we know the net force in the x direction to get its acceleration. Okay? So, next step is to solve for that force of kinetic friction. We're going to use our force of kinetic friction is equal to mu sub k times the normal force that we just solved for. So we've been given in our question the coefficient of kinetic friction. We know it is 0.500, no units because it's a ratio, times our normal force that we just solved for, 151 newtons. And that will come out to be 75.5 newtons. So what that's saying is that the force in the opposite direction to the applied force is this strong. So if we want a sum of the forces in the x direction, we can do the force applied in the x direction, which we solved for with cosine in the beginning, minus the force of kinetic friction. Okay? And that we can put opposite mass times acceleration in the x direction, because remember that this right here is equal to this, force equals mass times acceleration. So since we're in the x direction, we can make it equal to this, and then we can solve for our acceleration in the x direction just by doing math here, plugging in the numbers that we have. So we have a force, let me grab my little eraser. The force applied in the x direction, which we solved for at the beginning, was 77.9 newtons. And the force of kinetic friction that we just now solved for is 75.5 newtons. And then the mass we know is 20 kilograms. So let me just try and clean things up here for you. Our final equation is going to be acceleration in the x direction is equal to that force applied that we had, 77.9, minus the force of kinetic friction, 75.5, all divided by the mass, which is 20.0 kilograms. And since newtons are kilograms times meters per second squared, that checks out. We're about to cancel out the kilograms of the newtons and wind up with a unit for acceleration, meters per second squared. So if you do all of this math, your acceleration in the x direction is going to come out to be 0.12 meters per second squared to the right, which is why it's positive. Can you follow me on the steps that we did?
In the beginning I did, but towards the end I didn't really know we were getting this stuff.
So we started by resolving the force into its x and y components, okay? And then what we did was use the fact that there was no movement in the y direction to set that against 0, and then take the forces that we did know, the y direction of the applied force that we solved for, and the force of gravity to solve for the normal force. And then we can take that normal force and put it into our equation that we have to solve for the force of friction, and use that to solve for the force of friction, which is traveling opposite our applied force. And then summing those up gives us the total actual applied force in the x direction, which we skipped the step of summing those and plugged it straight into the equation of force equals mass times acceleration, because we had that. We knew that if we subtracted them, we'd get that applied force. So we just plugged those in, and then we divided by the mass to get our acceleration, just like you would a normal problem where they gave you a force and a mass and asked for acceleration. There are more example problems like this on page 141 of your textbook. So they are good ones to work. Some of the answers to those will be in the back of your book to check, and if you don't have the answer in your back of the book and you want to check with me, I have the answers for them. If you get stuck and you want to work one with me, I'm more than happy to work one with you if this is making you uncomfortable. There will also be some practice problems similar to this in your homework for today, so you can try them there too. All right. That's enough of the example problems. Let's talk about the last little bit of our notes here. Air resistance. So far, the forces we had talked about were the normal force, friction, gravity. Did we talk about gravity? And then now we're doing air resistance is the last one. Okay. Air resistance is a type of friction. So you could technically shove this under the friction category, but we put it in its own group because people sometimes forget that air resistance is friction because one of the surfaces, air, you cannot see. But it is the force of friction that happens between a surface and air molecules. Like other types of friction, it acts in the opposite direction to whatever your applied force is. When air resistance and the applied force are balanced, then your object will travel at a constant speed, or constant velocity, I should say. So if the force of air resistance is balanced, then that object can travel at a constant speed. So if you have set your cruise control and you are truly traveling at a consistent velocity, then the applied force that your car is putting out is enough to balance both the force of kinetic friction from the road acting in the opposite direction and the force of air resistance acting in the opposite direction. For falling objects, this velocity at which objects, the applied force, which in the case of a falling object is the force of gravity, and the force of air resistance is equal, is called terminal velocity. This means that an object will fall and it will continue to accelerate, so it will continue to fall faster and faster and faster until that force is balanced by the force of air resistance. You will still obviously continue to fall, okay, but you will not increase the rate at which you fall. You'll fall at a constant velocity. So there is a velocity at which you will stop falling faster. You're not going to stop falling because air resistance isn't going to cancel out the force of gravity, but at a certain point it will cancel out your acceleration. Interesting fun fact, squirrels cannot die via falling out of trees because their bodies are built to handle the forces that are equal to the force of hitting the ground at their terminal velocity. So they're also very, very, very good at catching themselves and displacing force and things like that. But their bodies are built to handle the kind of stress that happens when they hit the ground at their terminal velocity. So falling out of trees isn't dangerous for them because at a certain point they don't fall any faster and their bodies can handle that speed. So it's a pretty great adaptation for a tree-dwelling animal.
Does that include when they're babies?
I don't know if that includes when they're babies or not.
Because with their bones developing.
They snap.
All right, last thing we're going to talk about today, fundamental forces. There are 4 fundamental forces that drive all motion in our known universe. They are electromagnetic forces. Electromagnetic forces is kind of a bundle term for any of the electric and or magnetic forces caused by the particles inside an atom. So the fact that those are positive and negatively charged, okay, those forces, we call those electromagnetic forces. So any oppositely charged things or any magnetic things, those forces fall under electromagnetic forces. There's also gravitational force, which I don't have a lengthy description for because you all know what gravitational force is. It's the force of gravity between two objects. Then there are strong nuclear forces and weak nuclear forces. Of these forces, strong nuclear force and weak nuclear force are actually the stronger of the two, the stronger two of the four. They're actually pretty strong. The problem with strong and weak nuclear forces is that while they are very strong, they act over a very short distance. So at a microscopic level, they're very influential. At a macroscopic level, they don't affect our everyday lives so much. However, electromagnetic forces and gravitational forces, while weaker than the nuclear forces, are actually acting over much larger distances and are therefore able to impact the world that we see and are largely responsible for the forces we observe at the macroscopic level. So if you're observing a force, it's probably caused by gravitational force or electromagnetic forces. We don't think about the fact that electromagnetic forces are causing things, but friction is an electromagnetic force. You think about it as two surfaces that are rough passing each other, but even if you had perfectly smooth surfaces, they would still have friction between them because friction at that level is caused by the attraction between particles. So electromagnetic forces everywhere, all around you, affecting everything you do.